Okay friends, so this is another question on laws of motion chapter. In this question, as you can see, there is a wedge onto which a rod is kept and the rod is supported horizontally. So the rod cannot move horizontally, it can only move in a vertical direction, right? And what is the constraint with the motion of wedge? The wedge can move only in the horizontal direction, right? So motion of the wedge and motion of the rod both are constrained here. Right? So let us take one by one both of the masses and draw free body diagram, and then we'll write the equation. Now the purpose of solving these questions is to get the equations right. Fine. We will not solve the equations entirely, but we will apply whatever basics we have learned till now and get our equations in a correct manner. Fine. So let us draw the free body diagram of MA mass. So this is MA, right? Now as it moves down, what do you think will be the forces on MA? One obvious force that comes in your mind is gravitational force, right? It will be in vertical downward direction. So this is MA into G. What else force? There is another force which MB applies on MA, and that is normal force, right? Whenever two surfaces are in contact, there will be a push from one surface to the other surface, right? And it will be along the normal direction. That normal must be common to both the surfaces, right? So there will be a normal reaction which is perpendicular to the contact surface. So we will get a normal reaction like this. Any other force? You see that there are two supports. These two supports will exert horizontal forces, right? Let us assume that the net horizontal force because of these two support is this. Let us say this is Fx. We don't know what is the value of Fx, right? So we will take our coordinate axis, this as x and that as y. Now our next step is what? The next step is to resolve all the vectors along x and y directions, right? You can see that fx and mg, they are already along y-axis. There is no component of these two. No, mg is along y-axis and fx is along x-axis. So mg does not have any component along x-axis, and similarly fx do not have any component along y-axis, right? But normal reaction makes some angle with the x-axis. It will have a component along y-axis as well as along x-axis. So if we take the component, we'll see that normal reaction is making what angle with the x-axis? It makes 90 minus alpha, right? So horizontally it will have n sine alpha, and vertically it will have n cos alpha. Right? Now since you have resolved normal reaction along x and y axis, you don't need to show the normal reaction now. So I can just erase the normal reaction. Right? This is the situation. And what do you think the direction of acceleration will be on the rod? It is constrained to move vertically down, right? So let us assume that its acceleration is a1 downwards. Fine. So now let us write down equations of motion along x and along y direction for the rod. So along x direction you have what are forces? N sine alpha minus fx, right? Is there any acceleration along x-axis? There is no acceleration, right? So this will be equal to 0. And along y-axis you'll see that there is mg force, there is n cos alpha force, and this will be equal to MA into A1. Now the way we write Newton's second law equation of motion is we take direction of acceleration to be positive. So that is why I have taken mg to be positive, and opposite to direction of acceleration, which is n cos alpha, it is taken as negative, right? So these are the two equations. Let me mark it as equation number 1 and equation number 2. Fine. Let us now draw the free body diagram of the wedge. Okay. So this is how the wedge is placed, makes an angle alpha. There will be of course a gravitational force on the wedge whose value will be mb into g, right? There will be a normal reaction from this contact surface. Let us call this as N1. What other force will be there on mass mb? Now you'll see that there is a normal reaction which the wedge was exerting on MA, right? So according to Newton's third law, MA will also exert normal reaction on MB in equal and opposite direction, right? So normal reaction will be like this. This is the pair of normal reaction which MB exerted on MA. Fine. Any other force you can see here? Had there been friction between MA and MB, there would have been a pair of friction force also. But right now we are assuming the surfaces to be smooth. Okay. So I'll just draw acceleration vector, which is of course horizontal because it is constrained to move horizontally, right? Now for this particular case, we can take our xy axis like this. Fine. We'll see that normal reaction, mg and acceleration, these three vectors are already along either x or y direction. We need to take component of normal reaction along x and y axis. Okay. So if we take component of normal reaction along x and y axis, what axis normal reaction is making with the x axis? This angle is alpha, right? So this will be 90 minus alpha. So the component of normal reaction along x axis is n sine alpha, and in vertical direction it will be n cos alpha, right? Now normal reaction is a sum of these two, so I don't need to show normal reaction in the free body diagram now. So I can as well remove this, right? Now you can see all the vectors are aligned either in x or y axis, and now we can use sum of all forces along x axis is mass times acceleration along x axis, and a similar equation along y axis also we can write. So let us try doing that. So along x axis the net force is n sine alpha. Is there any other force? No, there is no other force. So n sine alpha will be equal to mb into a2, right? Let us call this equation number 3, right? And along y-axis you'll see n1 minus mbg minus n cos alpha is equal to 0. Fine. So we have 4 equations. That these are Newton's second law of equations. Let us count number of variables. We have normal reaction, fx, a1, a2 and n1. So we have 5 variables, but right now we have only 4 equations. So how do I get the 5th equation? At the start of problem we have discussed that both motions are constrained as well as they are related to each other. So we need to find out what is the relation between motion of MA and motion of MB. That will be our 5th equation, and that is a constraint relation, because when this MB is moving, MA will come down by a fixed amount. So there is a relation. So how do I get that relation? You will get that relation here by assuming that, by assuming that the wedge moves a little bit in x direction. Let us assume MB, the wedge moves by x. So this is the motion of MB. Okay, if this is the motion of MB, the rod must move exactly this much amount, isn't it? The rod will move as the wedge is moving in right hand side. So what is the relation between x and y? You'll see that this is a right angle triangle, right? X is horizontal and y is vertical, isn't it? And this angle is alpha, so this is also alpha, right? So tan of alpha will be equal to y by x, right? So I will get y is equal to x tan alpha. So this is the relation between their displacements. If I differentiate this equation 2 times, I'll get the relation between their acceleration, right? So if I differentiate y 2 times, I'll get acceleration of MA. If I differentiate x by 2 times, I'll get acceleration of the wedge. So the constraint relation will give me this equation. We have taken acceleration of wedge to be A2, which is along x direction. So I'll get A1 is equal to A2 tan alpha. Fine. So this is the 5th equation, right? So now we have got 5 equations and 5 variables. So we can now solve and get all the required variables value, right? So thanks for watching the video. We'll continue with this series and we'll take up a next question going forward, right? Thank you.